Okay, good morning, everybody. We were supposed to start a bit earlier, but you know, that's life. So welcome to this last session. Well, almost last session. So our first speaker is Fabio Ciotti from University Tor Vergata, talking about at the border between zoology and artificial intelligence in a way. And so, yeah, thank you.
Yeah. Yes, a little bit about me. I am actually coming from literary studies. I am a theoretician of literature that has been playing with computers and algorithms since the very start of my career. So since the thesis, I analyzed a small novel by Pirandello using statistical tools in the 1991, so it was quite early. And then I always have been in the field that today is called digital humanities, that is the interaction, intersection, and whatever between humanities and computing. Namely, I am, of course, specialist in literary studies, so I have analyzed text using various approaches. For many years, I was in love with ontology and formalization, so we applied ontological reasoning to model structure in text, either single or collections, of course, with the application in the domain of digital objects management in digital libraries and digital archives. And then in the last years, namely because of the fact that a great scholar in history of literature, this Franco Moritti at Stanford, started this thing that we call distant reading, that is the idea of giving up reading text to understand them, but taking many texts, possibly thousands or even millions, if it is possible, and applying to them text mining algorithm to understand something of literature and culture at a scale. So trying to see if there are wide or long-term phenomena that can help us understanding what literature is and how literature interacts with the rest of culture. And this is now a well-established subfield of digital humanities. Some say that it's quite distinct from that, but okay, these are kind of theoretical debates that are not, of course, at stake now. And of course, in my traversal of the computing domain with my humanistic background, I have come to meet large language models that are the talk of the town. So I obviously had to understand what was going on and how they could help us understand culture, literature, in particular, but culture in general. And also, this also revived some of my lateral interests that are the philosophy of mind, that I've been not as a professional, but I've been working and reading and trying also to apply to my ruminations along my career. And since these objects are quite really interesting philosophical objects, in the last 6-7 months, I've been speaking about what LLMs are to my colleagues, but also try to find some philosophical underpinnings to understand what is going to happen. And this is one of the last outcome of my musing, that is stochastic of all true believers, and the subtitle is on language models as intentional systems. Maybe you haven't heard about some of the names that I will cite. That is Daniel Dennett, that is the philosopher that has invented this idea of intentional systems. And that was sort of my philosophical guide, so to say, because I love how he treats most of the most complex problems that are regarding our capacity of as cognitive agents, and also trying to give an explanation that is entirely naturalistic and materialistic, so that trying to avoid any presence of unexplicable characteristics of even the most complex characteristics and features of human cognition, and seeing it in relation with a very, very long evolution that started from bacteria and arrived to bat. That is the title of one of his most famous books. published some years ago. I am not a professional philosopher, so I use it more than working on it. And this is what I've done here. The other picture is the great picture realized with, I don't remember if it was Stable Diffusion or Dali, or, but anyway, a great AI artist that produced this representation of a mechanical parrot. You see, the parrot is actually a robot. And why? Because the most famous article that is debating the on the negative, the characteristic of large language model is the famous article on the dangers of stochastic parrots by Bender and company, that has been cited, has been the most cited article about large language models in absolute, even more than the technical papers. And now I will, come on. Yeah, I'm working on the, I must, no. The problem is that, of course, come faccio? Giustamente. Oh, come on. Yeah, presentation. Okay, now it works. No, because I have to put on the first stage the presentation, not the representation of the presentation in Zoom. So, first of all, starting from probably I will jump some of the slides because most of you knows very well what is going on in these models from the technical point of view. But there are some aspects that are quite interesting and that are connected to my more theoretical arguments. So maybe you will be bored by some of the part of my my talk, at least those of you that knows very well what is a transformer and how it works. Anyway, starting point, AI hype and the development of these models, and in particular the deploy of ChatGPT that has been quite transformative events, both for what it means really, and mostly for what it has created in the Imaginarium. As anyway, revitalize the debate about both scientific and public about artificial intelligence. That was something that has had a long history that was almost forgotten for almost 20 years, and then starting from the first decades of the 2000s millennial have been reactualized with the introduction of neural networks, with the reintroduction of the ability to use really neural networks. Also, neural network, as you may know, is something that has been invented in 48, or at least thought of in 48. And as usual, this debate is characterized by the classical integrated versus apocalyptic position. And this happened, this is interesting, quite interesting. This happened both among the insider, the experts. You heard about Benjo or other people that has done the history of this technology that are really believing that we are in danger of extinction because of AI. And they are true believers in this thesis that can be, I mean, looking at that as of now can be quite weird. And there may be some also cultural reason for that, especially for the position that comes out in the US and in general North American culture. But anyway, and they are wider public, so we always read the danger of extinction because they are going to overtake us and take the power, just like happens in Matrix or Terminator or something like that, or more on a smaller scale, what happened in HAL with HAL 9000 in Space Odyssey, and these positions varies along in a spectrum that goes from the in set parentheses is because there are a kind of double suppositions in enthusiasm. That is, there are people that really believe that this is actually we will have in 10 years or 5 years AGM, that is general artificial intelligence. Other people say that these are great tools. They have, for instance, this is more or less me. They present strong aspects of intelligent behavior. Of course, we have to define what it is. Okay, we will see some of these problems can be solved somehow, some not. So we have at a certain point accept that the definition is an internal part of a scientific discourse, and on the basis of the definition from which you start, of course, you can develop an entire theory. Then, so there are the enthusiasts, more or less enthusiasts. Then there are the strong skeptics that says that these things doesn't work, that makes a lot of error. Then there is something that is a position similar to the strong skeptics, that is an a priori devaluation or dismissal. And these are very often based on anecdotal accounts of what these kind of tools or agents, whatever we may call them, does. And I think that Bender's article is quite in this position. So saying for various reasons, for cultural, theoretical, psychological reason, there are eminent scholars. Chomsky is something like that. I mean, he said this in a famous article in the New York Times a couple of months ago, say that these are not doing anything that is really important from a cognitive point of view. They are stochastic paradox. This again is a metaphor used by Bender. And then there is, of course, the later part that is unjustified alarmism. Unjustified, again, it's justified on certain side about ethical, political, social impact, and sometimes unjustified, because we are not going to lose millions of work positions. But it is true that a couple of weeks ago, the head of the build decided to lay off something like 400 journalists and other people working in the various journals and publication of the firm, and to substitute it with AI. So this will have an impact. And this has been announced by other publishing houses. This is going to happen in the translation industry, or so. But of course, we are not going to see something that was, I don't know, similar to what happened in the first industrial revolution. The problem is that this transition is affecting, for the first time in history, the intellectual work. That is, innovation has always substituted manual work, even highly complex and specialized manual work, but never affected the intellectuals. And in this case, the intellectuals are at risk, and they react and they write on journal and whatever. I've been in many meetings organized by, for instance, the Italian Association of Journalism, in which I was called as an expert, so to say, and their fear was they are going to substitute us. And as I said, it's not totally true, but it's not totally false. And then there are worst case scenarios, addiction, that is people that really believe that catastrophes are going to happen, and extinction will be a real menace by the next 50 years, because of the fact that these tools, as you can see, are really at a certain point willing to take the power and maybe use us as a batteries, as in Matrix. Okay, I'm only losing too much time. I will concentrate on this position that is theoretical, that is not in relation with the social or future perils of AI, but this is a criticism about what they are actually. So why we should, from one side, we should not be too much worried. On the other, we should be very much worried. And the article was published in 2020 by Bender, and then by Tebru, that was the girl that was working at Google, that was fired after the publication of this article. She was in the ethical committee of Google. And McKimmel and Mitchell, that is another researcher that has published quite a week ago another article in Nature that was criticizing the way in which we assess the intelligent capability of LLMs. For instance, the adoption of tests that are used for humans, and that probably the LLMs have read, at least GPT have already read. We don't know what they have used, or we don't know totally what they have used, because this is also another myth. There are some part of the text that has been used for the learning of GPT that are well known and can be downloaded by any of you. So you can use at least half of the data that has been used to have GPT. The other half we don't know, because they don't tell, and they have decided not to tell anything and since they realized that they had in the end something that had a value from the economical point of view. Anyway, the paper actually is a paper against the ethical and political perils of GPT. So the idea that they can be too big is that in this way they can have, of course, a lot of biases because of the data that they are reading and so on and so forth. But the very thesis that I will concentrate on is a more theoretical thesis that was already advanced by Bender with Keller in another article published 1 year before, that is Climbing Towards NLU on Meaning, Form and Understanding and the Age of Data. And the basic thesis is this. This is the starting point. Text generated by the LLM is not grounded in communicative intent, any model of the word or any model of the reader's state of mind. You can tell, okay, a coherent meaning. And I underline the topical phrases because these are signals of what I call a sort of revitalization of the ghost in the machine thesis. So they are, we tend to interpret them as they have a meaning inside their functioning or intent. So it is an illusion that they have meaning or they have human understanding and so on and so forth. This is an extract from the Stochastic Parrot article. It's that's the page if you want to give a look. The rest of the article is actually more based on this other kind of problem from the ethical and societal issues. So what this kind of this has been repeated many times in many ways by other scholars, philosophers, linguists, Chomsky, for instance, and of course, it's also a thesis that you can find very often repeated in journalist articles that are not really specialists, and they simply don't understand what they're saying, but they repeat this kind of phrase because it's very easy. Especially the parrot metaphor has been quite successful. One of the most important memes in the last 10 years. 5 years, let's say. So the first idea is that saying that they are mere stochastic oversimplifies the capacities of these models and the depth of their linguistic abilities. The assertion that are stochastic parrots, that is, that they are stitched together sequences of linguistic form in a hazardous way, belies the inner working of the transformer Bayesian model. For instance, these models are not simple string search and combinatory mechanism, as most of people seems to believe, and even specialists sometimes seems to believe. They are based on complex interplay of the attention mechanism. That is, for me, one of the most important aspects of these tools, especially the last generation models, because transformers with attention is something not new. It was published as an article by Devlin and others in 2017, if I don't get it, remember bad. So it's something that is already there on arXiv, moreover, so you can simply take the paper on the arXiv and read it, and maybe try to build your own language model without having to pay any fees or any royalty to anybody, based on widely distributed representation, real number, as far as we can represent real numbers on finite tools, of course. So claiming that these are pure stochastic oversimplifies the way in which they work. And especially they oversimplify the impact also of the second phase of the learning process, that is fine-tuning, and especially the reinforcement learning, and I will speak about this a little bit later. Second, and this is a more theoretical aspect, I already anticipated, this thesis, the parrot thesis, assumes key concepts as real human understanding, communicative intent, theory of mind, word model, without providing a clear explanation or definition of those concepts. So they play an important role in common sense reasoning, of course. And we attribute this kind of use this kind of words or similar words in our discussion and about mind, what you think, and so on and so forth. But they must be really explicated in a Carnapian sense when you use them in a scientific context. So what is happening is, at the end of the game, this kind of arguments share a sort of ghost in the machine thesis, or commit strongly with these theses, and are positions that are spread over a spectrum and goes from neo, not so neo, but anyway, Cartesian dualism to neo-vitalism, or even metaphysical neo-spiritualism. This is something that we cannot explain because it's inexplicable. We cannot understand consciousness because something that we cannot, or for instance, Searle says that, but also others, says that consciousness is something that is physically realized, but at quantum level or at some other mysterious level that we cannot really understand. It's a sort of fifth force in nature. And again, it's something that we cannot explain because it's being a primitive, you cannot explain a primitive. The Parrot thesis, of course, overlooks the emergent capacities of the large language models that were, most of them were not foreseen even by the people that have built them. So they have not been explicitly not programmed, but even teach to do some things. But they actually can do them. They work very well in translating between languages, in summarization, in having a kind of rudimentary, but not so rudimentary reasoning capabilities. And these are not an extension of their training data, but in a sense demonstrate a level of understanding. So the metaphor of the parrot that simply repeat what is heard without understanding is not, to me, a good metaphor for characterizing LLMs. Okay, I will jump this one because you know very well, but it is important to remember that what we are seeing now started since the 43 with the famous article by Warren, McCulloch and Pitts that for the first time used the metaphor, the artificial neuron, that was actually only a logical gate, but was using the metaphor of artificial neuron. Then the famous Rosenblatt experiments with the perceptron, that is actually the first idea of a neural network. And okay, you know this very well, so I can skip this one. What is a neural network? Actually, that is, and the various level and the various types of networks that, again, something that you know. One important thing that you know, but I want to stress, is that these things cannot be programmed. That is, you cannot program, and this is something that is quite interesting also from the computational point of view, because usually when you use computational tools, you start from looking at the problem, then you try to make a formalization of the problem, then you implement into a deterministic program that, using a language, a programming language that do what is expected to do, and you know very well what it should do, and if it doesn't, it's because you have been wrong. So you have been doing something wrong, and in this case you are trying to show what the system should do and approximate an optimal behavior. You were raising your hand? Yeah. Yeah.
So the fact it's technically incorrect that they cannot be programmed. So in the 80s and 70s, people were actually originally programming neural networks, which was extremely inefficient. And to a large extent, the reason why nowadays neural networks are successful is because we moved away from programming them. But even nowadays, there are still specific classes of neural networks where people do actually program them.
Yeah, this can be done, of course, but when you have billions of parameters, that's simply impossible. And the most efficient network in whatever application you may imagine are made usually of many, many parameters. So I think it's quite hard. That is true that there are architectures. That is something different than programming, probably, because a transformer has an architecture, and the various kinds of subset of network of networks are in a certain sense programmed, or at least devised in that way. So they have the transformers part, then there is the feed-forward part. So it's not totally out of control. It is, but at the end of the game, most of what we have been doing in the last years is because we have abandoned the idea of programming them. But also in the McCulloch-Pitts idea, there was an idea of a logical gate fundamentally. It was not different from the logical gates of the von Neumann machine. And anyway, this is the way in which we use them, and the capacity that they have is based on this. So, and you know very well that this is a process that is based on a sort of measurement of the distance between expected behavior and actual behavior of the net, and then you have a way to adjust the parameters or weights of the connections, so that at the end you have an optimization of the behavior of the network that approximate it sometimes actually does what you wanted it to do. Okay, GPT and its brothers are this kind of special networks that are transformers, and okay, we know what they do. They are based on another great idea was that of embedding. That is again an idea that was floating in the air since many years, but actually was for the first time realized by the famous article by Markov and others in 2013. Is if I don't remember badly, it was published, and again it's on. It wasn't accepted in a conference. I mean, one of the seminal articles of the AI revolution wasn't accepted and was published on their site for that reason, and then they built on that the first models based on embedding. At the time was only lexical embedding. Then someone realized that you can't have a real language processor if it cannot sort of represent text. So it's something like the step from the linguistic of sentences to the textual linguistics in the history of linguistics. So we cannot understand how text works if you don't take into account the world context. And the idea, theoretical idea, was there since the 50s, because the idea of the distributive semantics was formalized by Firth. It is said, and he actually cites Wittgenstein, meaning his use. I am sure that Firth simply misunderstood Wittgenstein, but to understand well Wittgenstein is quite a complex issue for even for philosophers. So, but anyway, the idea that language is used for Firth was language is the the meaning is all the context in which a word or a phrase is actually used in linguistic productions. So if you want to, he said the famous motto that if you want to understand the meaning of a word, you must simply look with which other words that word is goes around. In Italian we say dimmi con chi vai e ti dirò chi sei. That is more or less the basic of the tell me who are you, with whom you are friend, and I will tell you who you are. That is more or less the basic assumption of this idea. And this idea of translating the meaning in this sense of meaning, that is the use of language in a real context, in a vector of real numbers, was quite game-changing, because it actually worked. The first experiment with the first language models were able to make analogous reasoning. For instance, if the king of the UK is that, now who is the king of I don't know, Spain, and so on and so forth. It was not efficient, so at a certain point this idea of transformers came out, and the transformers was interesting because they solved the problem of efficiency in computation. Convolutional neural network, not convolutional, but recurrent neural networks are very computing expensive, and they do in theory something similar to transformers, that is trying to take into account the fact that a text is a series of linguistic token one after another, but using that approach couldn't expand the number of words to look at. And with transformers, this limitation has been overcome, and it worked with this idea that is quite interesting of attention. Again, the words are used in a probably very simplistic way, but this is something really interesting, because attention is a way to understand why after it, there should be something, a word on the basis of what has been said before. So the attention mechanism is quite complex. I never really understood the mathematical mysteries behind attention mechanism. I tried to read the paper 20 times, and actually, but the very idea is that there are some parameters that you can measure, that you can calculate, not measure, on the basis of the numerical representation of the input, that says why it can be connected to a robot more with a certain, of course, probability, more than to mass or whatever. Okay, and in this way, but this is not only this is a classical co-reference that is quite the most basic way of co-determination of meaning, but it can do much more. And then there is the idea of generating a set of probabilities for all the vocabulary of the model, so that there is not a single outcome. Actually, what the set of transformers with attention does is providing the probabilities that each of the 50,000 or 60,000 tokens, that again is not words but tokens, and it's something different. But anyway, let's take this simplification. So they say, well, we have a vocabulary after this phrase or sentence or even long text, the probability that you will have one of these are this and this and this. And then the actual choice is done by sort of stochastic selection that is controlled by the famous temperature hyperparameters. And this is the real only part that is actually stochastic in the process, because the first part, the attention, is quite deterministic in a sense. Oh, what is interesting, that these models are not only transformers, or they are transformers, and for the 90, but this is a slide that I took from a presentation by Andrew Karpati, that is one of the guys that is working at OpenAI. And this explains very well what is happening when they train something like GPT or PaLM, PaLM2, and the other one from Closure. I don't always remember the name, but anyway, the other models that are around Meta has distributed their own model just a couple of weeks ago. The only one that is open source, actually. So this is the pre-training that is based on a self-train process, and this is the most important. It takes thousands of GPUs, takes a lot of months of work, it requires a lot of energy, and we know that. But this is the beast. There was another famous picture about LLMs in that had a beautiful face. Then beside the beautiful face, there was a Cthulhu monsters like that is because the base model is actually something that you cannot use. Because it can say anything, and the output of the base model is almost unusable. And then they have phases of fine-tuning. The first one is classical supervised fine-tuning. They have some answer and question and answer that are prepared by specialists, and they use it to fine-tune the model. And then there are the phase of the reinforcement model, modeling, learning, and it is quite interesting. This quite marginal part of the learning, but at least for me, for many other scholars, these are the really game-changing aspect in these large language models, because in the first phase, the models learn how language or languages work, looking at thousands of billions of millions, or we don't know how many examples, using an intelligent trick. That is, you don't have to tell what is the right word to put after a sequence, because it's actually in the sequence. So they take a text, chunk it in sentences, say, they ask the model to read the first n words and try to provide the last words. And that is the target. At the start, it simply says bullshit. Then they measure the difference of the expected. They are vectors, so they can measure the differences in numerical term. And then they backpropagate the error and try to adjust the, and then they do it n times. We don't know what is happening with GPT because again, they are not telling us anymore anything. And
Fabio, sorry, we have 5 minutes.
Fabio, unfortunately, we have this half an hour mismatch that we have to recover somehow. And
I've done using some practical problems in coding design. Very problem, narrative application that check like so using the script then mathematical something like that. I did some gradual research with my point is then
Fabio, we must close.
But we cannot they can have a sotto and get those elements of the best division intentional system that we have developed in things like and try to separate conceptual theories from the elements of scientific theory of mind.
So maybe time more than for a discussion for a quick question, if somebody has a question. Okay, yeah, this is even better. So we will recover 10 minutes. So without further ado, I guess, to the second speaker, who is Vanchika Bava, and she will speak about chatbot in the museum. Please.
First of all, thank you so much for organizing this. I think it's, for me, very overwhelming in terms of the kind of different experiences and spheres of science that we come from, and that we can sit on one table and discuss very different concepts. And I would also like to thank Fabio for creating a very theoretical and philosophical overview of the topic of large language models, because in my talk today, I would be covering the more practical and application-based approach and what I really deal with as a researcher. So I'm just waiting for my slides to upload. I think it's on. So today I'm presenting the work of Stefan Schafer and his team, who unfortunately couldn't make it here today, which is good for me. And I would like to extend the thanks to Stefan and Aaron Roos, who are both my colleagues in the group Cognitive Assistance System, which is led by Tony. And the topic today that I'm discussing is chatbot in the museum, which is a very specific So the topic of chatbot in the museum is in itself very specific, but even there we have applications and challenges that are rather broad and seen in also other perspectives. So just to give you a small overview of what I will be presenting today, I want to first go through the project Chatbot in the Museum, CHIM, the ideation, development, and the results that we got from this project, and then move on to a second segment, which is a bit different from the main project in the sense that it focuses on small museums. I will come to how they're different later. And then I would like to give also my perspective to this by talking about the challenges that we see not just in the domain of retrieval augmented generation, which is the localization of research in terms of the application of chatbots in a museum context where you need very specific information before you can interact with the visitors. And at the end, I want to show a small demo from the current developments. And if you have any questions, please feel free to ask as I'm presenting. So looking at my audience today, I'm really sure that most of you would have had the experience of having a real human museum guide at some point. And if not, then yesterday was your chance, thanks to Francesca. But what is more popular today is to have audio guides in museums, and you probably also experienced that, and even chatbots. And I would like to think about how this experience is different from having a real human guide. And the main difference comes when, the information flow is one way, and we usually have pre-recorded sessions, and people can only use predefined inputs, and so they don't really have this freedom of choice, and this behavior is not very intuitive for the way humans interact. And I would like you to think about the time that you went to school. I think if you read a book and you went back home, you would probably forget most of the things that you read. However, if you discuss the topic intensely with your peers, you're more likely to remember the things that you discussed about. And in a way, museums do have an educational purpose, and that's the way we see it. And so the idea is as follows. Sometimes I don't want to be told anything, I just want to look. But then I do have questions. And with this idea, we gave birth to our baby Chim, chatbot in the museum. And just a little bit organizational background to it. The project was funded by BMBF and lasted 2 long years and already ended a year ago. So you have to keep that in mind. And we were luckily collaborating with Linon Median, who has access to a very big digital database of audio guides. And on the other hand, we also had Städel Museum on board, which it's a really huge museum located in Frankfurt. I don't know how many of you are aware of it. You are, but they basically have a very extensive collection, which spans over 700 years of European art, starting all the way from the 14th century, going through Renaissance, Baroque, to modern present-day art. And they were our gateway to a big community which was interested in such applications, which is really important when it comes to understanding human experience and how people interact with such applications. Because I think there are many scores and ways to evaluate how good the models are working, but when it comes to really assessing their application scope, you have to present them to actual humans and see how they feel about this. So before I beat around the bush, I just want to give a small demo of how the system looked. And it was an Android application. So basically you first had a system description, and then the chatbot guided the users through the whole thing. I hope there's audio.
Hallo, bitte zuerst auf alle Werke anzeigen, tippen und ein Bild auswählen. Dann können Sie Ihre Fragen stellen. Spracheingabe funktioniert, indem Sie kurz das Mikrofonsymbol berühren. Für schriftliche Eingaben unten ins Textfeld tippen. Fragezeichen müssen nicht gemacht werden.
That's the translation of the text that you see on the right in the application. So the visitors could select artworks from all over the museum, or they could also get
Bild im Stockwerksplan anzeigen.
And they could also guide the user to find where the artwork is.
Okay. Wenn Sie wollen, können Sie jetzt Fragen stellen.
So at this point, you could actually use the free text input or speech input to ask questions about a specific exhibit that you chose. In this case, das Mittagessen. So the people who did this project realized early on that the visitors don't usually ask questions that are answerable based on the content of the exhibits that are provided in the museums. So they ask themselves, what do the visitors ask? And broadly speaking, there are 2 kinds of questions that people come up with. First ones, which are termed as factual questions, which you see on the top. When was the picture painted? Is a bit easier to answer based on the kind of information that museums usually have. And this is usually structured information. On the other hand, there's also a big part of open questions that people ask, which are not directly answerable based on the factual information we can obtain from museums. And on the other hand, they also have multiple sources that need to be used to answer. So it's not a one sentence that really answers these kind of questions, and you have to think about how you can augment different sources together. So first, I would talk about the factual questions and how we dealt with it. Keep in mind that this is before the big LLM wave, when many open source models came up. So we used approaches that were at that time state of the art, I would say. And in this case, we created a mapping between the intents of the user and the structured information that was available from the Städel Museum. In this case, you can see the user asked, who painted it, and the model would then try to predict what category or intention this is, and then look at the database to query what kind of information is needed and augment to create an answer. But I think the highlight of this was still the intent recognition. And I have a small demo for such kind of questions.
Wie groß ist dieses Bild in Wirklichkeit?
Die Größe des Bildes ist 280,0 mal 450,0 Zentimeter.
So, yeah, I believe that was the correct answer. And now coming to the more tricky part, which is to answer open questions. We realized that actually dividing the context that we have available from audio guide texts into different content types increase the accuracy of the models. So if you provide the model with all of the content, it actually performed worse than if you would try to streamline the content that you think is more relevant. And we did that using then state-of-the-art word. And we basically looked at the context and tried to fine-tune it to predict where in the text from the audio text is the relevant answer, and then use that to generate an answer. And in order to categorize our text into different content types, we did an online pre-study where we collected questions from the community of Städel Museum for 15 exhibits in this case. And at this point, the people could only ask questions and did not receive any answer, but this was our way of understanding what do the people want to ask when they when they look at different artworks. And this helped us to define 12 different content types, which yeah, you can see that people are more interested in certain things like meaning or content, but there are also other things that exist. And this approach was also a part of the paper that Schaffer and Moos wrote, which also received the Best Paper Award. But basically it shows that we need some kind of domain expertise to know what kind of data is important to the user to be able to accurately answer those questions. And again, a small demo of the open
Wer sind die
answers.
Personen auf dem Bild?
Club Monet zeigt seine spätere Ehefrau Camille zusammen mit dem gemeinsamen Sohn Jean am Tisch. Am Fenster lehnt eine Besucherin und dahinter schließt eine Bedienstete den Wäscheschrank. Nicht zu sehen ist Monet selbst. Für ihn ist der Platz vorne mit der bereitliegenden Zeitung, dem Le Figaro, reserviert.
This is the actual context from the audio guide. So at this point, we did not generate a text. And I think the impressive part is that even though the approach, looking back now, seems a bit trivial, but it actually worked in practice. And I think that's important to appreciate. And it led to a field test that we had in the Städel Museum where around 100 participants were involved, and they basically moved around freely in the museums, and their task was to ask at least one question to 6 or more exhibits. And we wanted to do this to make sure that people do not restrict themselves with the first room they get into, and then we don't have a big variety. And in this study, we also collected all kinds of log data, including how the people interacted with the system. So the GUI interactions. And of course, we had standardized demographics surveys and user experience surveys, which were actually quite helpful in getting our results. And the people who also had the opportunity to give a thumbs up or thumbs down to the utterances of the chatbot. And we used that to further understand how the answer correctness is relevant for user experience, but also things like speech quality and yeah, many different factors, what kind of role they play in the experience of the user. And I would first like to point out that you can see here that people ask more questions to certain exhibits as opposed to others, but also we see that actually the answer correctness is not that high, which could also imply that the content that we receive from the museums is just not good enough. It's just not, does not have the answers. Of course, we could have better models, but in most of the cases, these questions are not restricted to this. People want to know more than what is provided in the museum. And we also have a very recent paper which talks about how user experience is dependent on different factors. So I want to now move to a very different use case, which is still a museum. And it's different in the sense that a small museum usually has a central exhibit. So as opposed to a big museum with hundreds of exhibits where you are allowed to move around freely and ask different questions, visitors usually come in and they are only concerned with one main exhibit. And there are different challenges that occur in such situations. So we had the opportunity to collaborate with HBK Saar, which is close to Saarland, if you know where that is, but I also brought a map because I didn't know where that is. And we conducted a series of chatbot seminars with students to give them the opportunity to extend our system and understand what kind of challenges are faced by rather smaller museums, which are not resource intensive as the bigger ones, and they don't have the resources to train the models themselves from the scratch. So we wanted to know how well can our approach also be applied to other smaller museums. And as you can see here, there's a very extensive outside area with parks and pavilions. However, the challenge that the museum faced was that people were interested in what's laid in the main building, which is a swallows. So it is quite an impressive large ground floor mosaic, which consists of different Roman art pieces. And what people usually did was they went in and they only visited this part and they did not have the opportunity to actually look around the villa and the other ruins that were recovered. And I also want to mention that what's special about it is that it was actually excavated and restored after the World War II, so quite recently. And the students came up with very interesting approaches, including gamification, also using guided tours in a way to promote the visitors to explore the area. And also some, they also took into account small talk because that's what people do when you give them a chatbot. I have a small demo here in the background, and you can also use the barcode because the chatbot is actually still available. And yeah, I think it was, the purpose here was really to involve students in such applications and provide them the tools, the state-of-the-art tools, because one of the models they used here was also Godel, which came out quite new back then, to produce generate the answers. And with this, I want to take a dive into the current challenges because, as I said, it's only been a year, but a lot has changed in terms of the resources we have available and the kind of challenges we have now. So I would like you to take a step into the current challenges now. And this area of science that we're dealing with, or the area of AI we're dealing with, is retrieval augmented generation, which is a bit different than end-to-end models in the way that you basically have a retrieval phase where you retrieve the relevant documents, and then you want to create a response based on this information. And this is very common and very sought after application, because a lot of times we would like our models to be grounded. It's definitely a quality by large language models to be able to answer open-ended questions, but in a lot of cases, we want our models to be grounded. And a big step that happened in this area was that now we're able to include very large context, which was a bottleneck back in the day, because you have limited input tokens that you can give to a model, also depending on how it is trained beforehand. And now that has increased quite a lot with the models that are coming up. However, not everybody has the resources that ChatGPT has. So we still deal with problems of limited hardware capacity, even with very advanced GPUs, because if you consider that autoregression requires the whole sequence to be present to decode the next token, and depending on how many billion parameters your model has, you have quite a high memory load, even for one sentence. And if you have large context like documents, the scale is very fast. And here are some tools that people usually use, people like me, Hugging Face or TGI and VLLM. And at the moment, we're trying to experiment with the new libraries that have come into play, which have a different way of how they handle this, how they serve the large language model. So they basically use something like paged attention, which is a very classical concept in operating systems and how they manage the RAM. But what they basically do is they try to load only the parts of the sequence which are relevant to the query, but also they use non-contiguous memory. So you don't reserve the whole memory at one place, but you rather divide your data into blocks, and then you reserve memory in different places. So you don't have problems like over-reservation, but also fragmentation, where if you have the memory block in the middle, you can't use the whole space. So that's something that we're looking at the moment, and these results seem too good, I would say. But you have to keep in mind that they're also limited by the kind of task they're applied on. And with large language models, in my experience, the results vary a lot based on which task you are doing, and also which data the model was trained on. And here they considered Llama, which is a relatively smaller model compared to other models that came out recently. And even with a 100 GPU of 40 GB RAM, it's quite slow with Hugging Face. I don't know who has experience. You must have used ChatGPT, but actually, if you post models through Hugging Face, it takes quite a few minutes to get a response, which is really slow for a real application. So these are the kind of practical challenges that we have, and this is quite promising. And at the moment, I'm trying to work with this. And then I want to come to another issue, which is, even though we are able to provide a very large context to the models do not use all of the context in the same way. So it's a very recent paper, I think it came out this month, but they basically showed that the information in the text that is at the start and the one that's at the end is used more efficiently to accurately answer the response. But in the middle, the accuracy drops even below the level which a model would have without access to this external document. And I think we still don't understand how the models exactly use this information, which brings me back to the project CHIM, which, even though it was a bit more primitive, has an idea of the domain context and tries to deal with how we can use the context a bit better. And at the moment, another approach that I'm looking at is how we can retrieve the documents in a more optimized manner, because at the end, it all comes down to the quality of context that we provide to the large language models in addition to how they're trained. And in this approach, basically, the classical approach is that you first do the retrieval task based on some statistical model, and then you try to check the similarity of the retrieved documents with the query that you received. And usually that's a bit limiting because you don't take into account the interaction details while you're retrieving. So the approach basically tries to couple these two features into one last step of re-ranking the documents. And I think that's the direction that applications in large language models are going, to understand how the domain data can be used a bit better and how it is used by the models. And with that, I want to leave you with the thought that there is a lot that we can get from large language models, but, oh, I'm sorry, there's a demo that I want to give you before I end it. So talking about all of these approaches, I have a small demo from another project, which is not in the domain of museums, but it does a very similar thing. So this is an example of a factual question. What is the presentation chatbot in the museum about? And we used a relatively large language model, Vigoni, to first retrieve the information and then augment this context to generate a response, which is new as compared to the approach I showed before, where we did not actually generate a response yet, but we only tried to use the context to be sure that we're not giving some irrelevant answer. But in this context, we see that it actually creates a very reasonable answer from the context that we provided. And on the other hand, I would like to show another demo, which is about the open questions that I mentioned before. Was gibt es zu Mittagessen? So what is there for lunch? And the context does not include information about that. Nothing, yeah. So keep in mind that it does not have any information about this. However, it's still able to create a response that is relevant to the conversation. So it says, unfortunately, I can't give you any information about the lunch because it's not on the agenda. Please contact the organizer, which is, I think, quite reasonable. So there's a lot of progress, and I think we really need to remember that the domain-specific context still remains very relevant when it comes to actually applying large language models in real-world scenarios. You can't completely trust them, and the power is in the quality of the data that we provide. So I think it's still important to know what the users need, what kind of data we use. And on top of that, I think the challenge that smaller companies or research academics are facing is that of hardware, because yeah, as I said, we need more efficient approaches of how we handle this.
Sorry, these are all work of parts. If you ask chat, give me a meaning of this picture. You get an answer?
At the moment, not. So it's only text-based. But there are models that do that, of course.
Thank you very much. Vanchika, it was very interesting. And I also have some questions in this direction. The first is, you have said at the beginning, of course, that an audio guide is passive approach, but
yes,
to a certain extent, also this one is sort of passive. I'm wondering if the users, the visitors can contribute somehow to feed the system or not, in what ways or not. The second question is about this question already posed. So it was very interesting, this scheme you presented, you know, the 12 content types of questions. By the way, this website where you have collected questions is open. It's visible.
Not anymore.
No, but it's very interesting. And here you have these different categories now: context, meaning, content. However, for art, content and meaning can be also overlapping between these two categories. And so that's another question. And the third question, it's about it's only text-based, so you cannot ask for other similar images, for example. So an iconographic search, something like that, that gives you other similar images.
Yeah, that's interesting. So at the moment in this project, it was only text-based and people could choose the image themselves that they saw. But we also use like Bluetooth to detect which image the person might be looking at, depending on which room they were in. Coming back to your first question, could you repeat that again?
If the public, the users can interact more in the sense to contribute to the explanations, to the thing.
At the moment, it's a bit challenging because the models, to be retrained, it requires, I think we all know that by now, that it really requires a long time.
I mean, it would be like Wikipedia. If everybody says something to the
yeah, that everybody's contributing.
Yeah.
I mean,
Wikipedia is surely inside the model. One of the few sources that all the models are using.
I think what we should put that in context in a way. Also, other people think and so on, which would require maybe full training of the whole model, but could be used actually, maybe even with an additional kind of collaborative filtering approach, to select actually the context better. I think this makes sense in a way.
Because this other trend that was already mentioned with the case of the students yesterday, the idea that the citizen science model, that the people can contribute, in what sense is compatible with the training of the machine from the internet?
I think at the training time, it's already considered because we do use the data that's scrapped from the web. But there's also the possibility of using dialogue history, for example, within the context. So it's basically how you fine-tune ChatGPT by talking to it. So that's definitely there because.
Well, what is interesting actually, which we also is, of course, when we have dialogue history, you could also have places. So things that are related actually to the array as people made and so on. This is something.
Exactly.
I guess so.
It signalizes
more temporal in a way and very individual. If you have something spatial, we say things that people have said in this room. Often the space, at least exhibits, has a meaning. They're not kind of arbitrarily arranged things, but things are related to each other, which might not be immediately present actually. Exactly. It's kind of more an implicit kind of thing, but of course that you could model through feedback and questions that people have implemented good at this, I guess. Interesting. But I'm not sure if Stefan is solvable, but I think it's interesting.
Yeah. I want to come to the question about the content and meaning. So in this case, content refers to questions like who is in the picture.
It's interesting because this matches some theories of art interpretation, namely one of Erwin Panofsky that thinks iconography is different from iconology. What is represented is different from the meaning, but this is all, I mean, the art historians contributed to this with you in the construction of the system and the questions.
Yeah, so the museum actually helped us with the annotation of, but it's again subject to how the different people think.
It would be great to have this website with the questions to see.
Yeah, I'm actually not sure if it's still hosted, but probably not because it was a false study.
But you should have the questions.
The questions for sure, yeah.
We can talk to Stefan.
Yeah, maybe. Yeah, why not? It's interesting for
Yeah.
us.
Should be kind of
Secret.
I think they would actually be happy to receive more questions.
I mean, the paper has been published, so
Yeah, the paper,
Yeah. Actually, it might also be the case.
We'll ask you then.
It might also be the case that actually it's open source. I'm not sure at the moment.
Question. First, have you fine-tuned the models, Vigoni or Riyama, or you just taken it as it is?
We fine-tuned it.
With your own data? Okay.
Yeah, without fine-tuning, it wouldn't work.
It wouldn't work because it doesn't know about anything about the data?
It was not as consistent, I would say. There were
So
in 10
you
minutes.
found that there was a great improvement in the quality of the answers with the fine tuning.
Yeah.
But we don't know. For Yama, it's actually published the data set with which they have been learning. But what was if you think the ratio between your data and the original data set that we know, at least for what they say?
Yeah, okay, so I think the difference is that in the end, we want to predict certain intents that are important for us.
But you fine-tuned the base model, or you did something like reinforcement or supervised learning?
We did reinforcement learning, actually. And yeah, I'm not totally sure of
because if you added some new content,
because we tried different things, and I'm not sure
more
which
kind
one.
of supervisory learning, because reinforcement learning is starting from what it already knows.
Yeah.
And so probably you added some knowledge using. Don't think that you did the base training, but probably. Okay, another. Are you thought?
We also used the context that we had. So the other experiment was in a different domain. And we also used the information that we had from other documents.
Okay, so another technical question. When you so you say you use the answer, then try to extract the context from and you put it in the prompt.
Yeah.
Okay, and you try to use vector database to model the context in such a way that you can first search the most. This is a classical technique for prompt engineering. That is using vector database in which you have bunch of text that are your context. You search first time, that is very fast because vector database are faster than LLMs. Then extract a bunch of prompts and then ask the model without losing, without putting all text, but maybe a set of text that can work better.
We did not do that yet.
Yeah, because in this way you can, for instance, if you have a whole article about a picture that is 10,000 words, you maybe can find what is relevant using a simpler vector representation.
Yeah.
Then you extract it as a prompt and the model thinks and reason about it.
Yeah, so in the first approach
without
with
giving
words
10,000 or 20,000 key.
Yeah, that's true. That's why we are looking at this re-ranking approach to understand how we can find the correct context.
So, thank you very much. We are. So, since we have to close at 12:30 and we have to regain this time, I would suggest to have a shorter break in spite of half an hour, 20 minutes, and reconvene here, let's say 11. No, 11:30. No, 11. 11. 5. Yes. Yes, 11:05. Okay. It's 11:02. Okay, so next and last session, opened by Vigoni, the research director at the institute that is called SIGN-VigoniRicerca, named after
doesn't make a big difference, yes. It doesn't really matter. In this context, I'd rather not be. Anyway, okay, so thanks a lot for being here. I'm just one of the last talks, so we are all very tired. Thanks a lot to the organizers and to all the colleagues and friends that were here. Some of them were known before, others are new friends, and I think that already is a fantastic result of the networking that we're making here and of the nice interplay that we're starting. So, as said, my institute is in the Department of Engineering and Communication Technologies, Energy and Transportation of CNR, the largest Italian research institution, not university, but research institution. And actually, our department is indeed the largest one. CNR is more than 1,000 researchers and 19 institutes. And these are the main research areas. And I highlighted computer science, applied math, because this is more or less where we're working with the institute. The research area that we're covering are mainly operational research optimization, computer science, and then control theory, a lot of data science, of course, which is all connected, biomedicine and bioinformatics too. We have a group of colleagues that work directly into the Gemelli Hospital and are mainly doctors and engineers who provide very interesting use cases and problems for us as well. And then, of course, in this context, coming to the topic of the talk today, artificial intelligence. Some projects that we're dealing with, the most relevant one in this context is this future of artificial intelligence research, on which I will spend a few more words later. This big project that we're dealing with, that funded by the Cohesion Agency in Italy, that deal with bringing intelligence to the management of cities, and we're now having two and maybe even more cities in South Italy where we're trying to bring these digital twins that should cover different aspects of the life of the city and integrate that. And then we also have an interesting project in health, because we are building digital twins for health for different types of diseases, mainly using organoids and organs and chips. And our task in this project is just to make the models that interpret the results of these new experiments. So this is more or less the general setting. I also am happy to spend a little bit on this big project, FAIR, Future of Artificial Intelligence Research, which is quite interesting because it's a big project funded by the Resilience Funds. It's lasts 3 years, quite some fundings, a lot of researchers, 350 official PIs, plus 100 PhD and 150 years of fixed term researchers that we're hiring exactly now. And the project has to do with a certain European philosophy to AI, I would say. That is, artificial intelligence systems that can interact and collaborate with humans, that are aware of the limits, capable of adapting to new situations, and are attentive to the impact they have on the environment, both the social and the general environment. So it's trying to bring a possibly more careful approach to AI. You see the different folks talk about integrity, human-centered, resilient, adaptive, symbiotic, pervasive, green aware, a very interesting line of research. We have a lot of people in research trying to make AI to have less impact on the environment. And then I'm highlighting this one because it's both when we are working with my institute, which is high quality AI, meaning that we try to make AI a little more high quality, improve the quality of it. That's I couldn't find other words of saying this. So this is the research group in my institute that deals with this kind of problems, mainly the optimization and computer science. So we have also Ipazia and Pythagora in the group. They give a lot of help, and but that's because they didn't want to put pictures because they're shy. So that's the solution. And say that, I mean, of course, what I'm presenting today is not my own work. Partly it's my own work. I'm taking parts from also surveys and other reflections on the topic. So I thank all of my collaborators and also the other people that provided the material and reflections to this. So the talk is about optimization and artificial intelligence. Whatever we said in this context about artificial intelligence, it's actually machine learning. So not want to substitute for the time being. I don't necessarily agree with that, with this change, but we can substitute artificial intelligence with machine learning in the context, and I don't think anybody will scream or complain about that. So what is optimization? Optimization is what is essentially one of the main purposes of mathematics. To make a model, to have a function, as simple as it is. But first of all, I also need to apologize for the technicalities that I will put in this talk. I couldn't help but having them. I tried to put them at the minimum. Whenever something is not clear, just don't worry, because I think it's not essential for understanding formulas. So in optimization, we want to minimize a function, given some constraint, given some physical concept of the value that we want to optimize. So example, we have a function, we want to find its minimum, and this function is variable that we want to optimize, can be free to range then all his domain, or maybe constraint to be in a certain space. And of course, this problem can be easy or can be difficult. Can be easy according to certain conditions that we love to study. Like, for example, when the function is linear or convex, or when the feasible region is a polygon, then it's something that is easy. We can do that, no problem. It may take a little time if the problem is very quick, but in general, when you have something like this, we can model this problem with very valuable tools. On the other hand, we can have non-linear functions in non-linear feasible regions, as we see here, that are more difficult to optimize. But optimizing happens to be, let's find the best solution according to the function, which is, for example, the minimum. And of course, we can have global minimum, local minimum. We can be trapped into some valley and stay there happily, not knowing that there is a greener valley just around beside the mountain. So this is the main problem we optimize. And then we have the most difficult problem when we have functions where the evaluation of the value of the function is bad. You can do it only with a black box, with experiments, for example, and even the establishing whether the solution is feasible or not may need a black box, something that is an algorithm that takes a long time. So these are the two extremes. So first of all, I would say that optimization is a problem, something that we have to solve. It needs algorithms and computers. The size of the problem matters, because the larger the problem, the more hard to solve it. There is an issue of solution quality. We can solve this problem exactly, and we can solve them heuristically. Exactly means I know that this is the best solution. I can improve it, and I don't need to search more. Heuristics means I may need to search for 5 times. I can find the Then let's go to machine learning now, which is called we can also do artificial intelligence. Machine learning can be framed in a very simple setting, like we have a function that we want to learn from examples. This meaning that we have x, we observe x and y. Y is our target variable, what we want to know, and the function depends on some parameters. And what we do, we find the value of those parameters that minimize some error. Here I put a quadratic error, which is quite standard, but as we will see later, there are other options for the choice that can bring different results. So this is a super simple setting. And of course, also here we can have physics and we can have machine learning problems with our standard reduction in a plane. You have x, you have y, they make up a set of points in the plane. You want to model your f of x, it's a line, you want to find the best possible line that reduces the error that you make. But equivalently, we can have a very much complex model where you have a neural network, we know about it a lot, we talked about it for the whole meeting. Input layer, our variable, multidimensional, lot of strange transformations inside the network, as complicated as one, and then we have output here. So we have x here, y here. In the middle, your theta here, it's a number of weights, of links, and neurons, and then they can be emotional, they can be recurrent, all sorts of possibilities. So solving this problem is equivalent to solving this problem, except for practically. Here you have a large number of ways that you can do this. From the data that you observe, your data. So at this setting, I just pose some questions about the relation between optimization and machine learning. And the first ones are, okay, machine learning, as we saw, works very well. We're all very surprised somehow nowadays how well it works. But we don't really know why it works. We're not so sure. There are approaches, theory, explanations, but we don't know whether the problem is well posed. We don't know whether the solution algorithm, whether we have or not optimal solution algorithm. Actually, for certain problems, we know that we don't have. We don't have the clearly defined objective function. And we observe, for example, a trade-off between precision and robustness, which is somehow baffling. Why? When I try to be more precise, then I make more error. This is strange, right? And that depends on the fact that we have noise in the data. But then there is the issue of whether we trust these systems, this machine learning system that we use a lot. Of course, we've seen beautiful examples of them. And we trust, nowadays, we trust them because they work. And that's a very good reason to trust them. On the other hand, if we assume, if for granted that they work, will we realize when they do not? I mean, if we assume that this thing is working well and we build on top of it, will we ever realize that something is not working as it should, or that we could make it work better? How can we establish that we cannot improve any further? These are important questions that don't have to stop us using machine learning in this setting, but still need to be considered by the scientific community. There is a lot of work on models, as a matter of fact, and we should question whether there is enough work nowadays done on the algorithms that solve problems. And so I will consider a little more what are the interplay between optimization and artificial intelligence. What can each of these branches of science do for each other? What optimization does for machine learning is very evident because machine learning is an optimization problem. There are some contributions that were given from optimization to machine learning that are more to be given now. And the contribution is very interesting and important. On the other hand, what I will also pinpoint today is some contributions that machine learning gives to optimization, and this is a less evident. It's a very fresh line of research, very promising. So I will try to give you a little glance of that. It's something that I think it's very interesting. And there is, of course, a lot of cross-optimization. So something goes from optimization to machine learning, but also from machine learning to optimization. It's a mutual exchange. And I will just scan a few simple examples to discuss this. Neural networks. I will not talk about subprefecture machines because it's too mathematical, grasp the meaning of it. Decision trees, mixed integer programming, and then heuristics, feature selection on zero norm and outliers detection, and that is a piece of work, and also meta network for forecasting. And in these little examples, I will try to give you a little taste of what are the interface with the organization and machine learning, and what is interesting within field of additional research that we'll do. So, first of all, backpropagation. Backpropagation is the method that we use extensively. I mean, it's the main method that we use in neural networks. Known as the workhorse of neural networks. It applies to all types of neural networks, different classifications and tricks, and very clever assumptions. And how it works, it simply takes a network, whatever. I mean, how do you make a network? Just assign weights to the arcs, to these connections. Random, for example, why not? We just take them from other networks, often mentioned today. And then you put your example here, you compute all the little functions that are here, you get an output. The output is not correct because you're actually using a training function, not output. You just can propagate the error using the derivative. So it's a very simple calculation. You just go back, decompute the arcs on going back, trying to fix a little bit the error that you just made. Okay, just for one sample. I do it for many samples. And eventually this converge. And this is ideally is called the stochastic. Sorry about that. Stochastic that we understand because it's done only on one element at a time. So there are changes in this function that are not taking the whole training set, but just parts. In the one extreme, it's just one sample at a time. Then you have mini batch approaches where you can take little parts of them. But in general, this is how it's worked. So having this backpropagation at hand and having it working very well, we have it in many different implementations, in many different settings. We get samples and we get weights, and these weights minimize or try to minimize the loss function that we have. This means that we don't know, according to the shape of the function, whether the solution is unique, whether it is the sparsest solution, meaning that uses the least possible number of weights, or whether the performances are affected by the shape of the network, whether there are many possible solutions to this network, to these weights. We're never sure that we get to the unique best solution of this network that minimizes the error really. So we should pose these questions, and if we can answer, would be good. Probably we cannot answer now because it's too complicated, but we still have to keep in mind that these are open questions for science and affect the results that we obtain when we use a neural network. So this is one open field. Another interesting thing that at least is interesting to me, it's something that has to do with decision trees. Decision trees are a very, very simple machine learning system that is used extensively. It's of course overruled by neural networks for many reasons, because they're very simple, but it has a nice advantage that you get out explanations. So it's one of the, actually, we're studying them a lot more now because they fall in the field of explainable methods because they obtain rules. How do they work? That's a very simple way. You get samples in your tree, and then you start dividing the sample, defining parts of the samples, creating rules on your data, with the aim of finding leaves, meaning terminal nodes of this tree, where the samples are all of the same class. And these leaves here represent an explanation of a certain number of samples. Now, this has a lot of heuristics implemented that work very well, very fast. But if we ask ourselves how we can find a leaf which is the largest possible and has a given level of purity, assume that you want to say, look, I want to find a leaf where all the red elements are contained, and I want to find rules that lead to the leaf, and I want this leaf to be of the maximum size. Well, that is indeed that complex problem to solve. You need to set up a minimum cost satisfiability problem, for example. This is one approach. And it's also, obviously, it's much more time consuming because it creates a different explanation. And this method that is based on this approach, finding this maximal covering leaves of the tree, has been tested and has been successfully applied in many bioinformatic applications because it beats the actual method of decision trees that are based on heuristics, although it's much more time consuming. And then when you have roots of this type that are associated to leaves of the tree, you may reason with them. You can make theorem, you can realize with some formal methods what are the extension of these rules, what are things that will never be accepted by these rules. So this gives a more rich and possibly interpretable information that you don't get, for example, from neural networks. Let's go now to the other part. I mean, what is that machine learning gives back to optimization? Well, it can learn to find solution of problems. This is a very new concept that you have a problem, but you do not solve the problem through its formulation, but simply looking at the solution. Sometimes it's very hard to do this because the solution don't give enough information, but now there are ways that we can provide additional information and things start to come into light. For example, we can contribute to the steps in exact algorithms that we use to solve complex problems. And these exact algorithms do a lot of steps, do a lot of search. And during the search, we can apply machine learning to improve the search. And we will see that hopefully in a more detailed way in a moment. So in general, you can have a training set which is composed of algorithm status, effect on the steps that you make, and then you can learn what is the right step according to the state of the progress of the algorithm to solve a problem. Or you would have, on a more higher level, a training set made of problem, parameters that are used to tune the algorithm, and the effect, and you can learn from this. And we will see a couple of examples of this now, because let me just have a very classical example, which is mixed integer programming. Again, you don't need to understand of this. What you need to understand is that this is a problem that can be defined on a lot of variables, a lot of constraints. It is a simple problem if you simply ignore this part. Okay, no, it's not with us. It's a simple problem if you ignore this part, and we will see later. But it's like problems of this type are normally like finding a needle in a haystack because they have a big combinatorial explosion. So, of course, we remember the example of the grain of rice for each of the squares of a chessboard. The number of solutions that you have to investigate grows exponentially, and it's very easy that you cannot solve this problem in a decent time. Nevertheless, they're used to formulate very important problems that we solve every day, like going from one city to the other, from a network of cities in the shortest possible time, delivering goods on a network, saving with a minimum number of vehicles. These are problems that are solved every day in your telephone, in companies, whenever Amazon gets to you and brings you something as a delivery. That is not done by machine learning. This is done by solving algorithm problems. A few years ago, we did this type of application for Agile Petroleum, it was still called that, to optimize the flow of the tanker over the water. And we showed with mathematical methods that they could use 25 instead of 27 tankers. Okay, and can you imagine the saving behind that? And tremendous, right? Not to speak about impact, pollution, consumption, etc. And you can understand this only by solving very complex optimization problems. Now, the key is that in optimization, we want to find the minimum of this system. And finding the minimum and proving that it's the minimum is very complicated. So how do we do? Normally, we have exact algorithms, heuristic algorithms, different methods that have been studied in time. And we see whether we can use machine learning to improve these techniques. And for example, we can. So we are proposing machine learning algorithms for solving different parts of these methods that are already established. and also to try and learn to solve algorithm problems without the model, but just from example, just from training. And one of such cases that I will tell now is about the search that I mentioned ground tree, which is still the comparable to looking for a needle in a haystack. The main trick in this case is to relax the integrality constraint, meaning that we are not looking for integer variables that have 0 or 1 in the simplest possible case, but these variables can have any value, let's say between 0 or 1 if that is the data constraint. And then we look for these things through branching and bounding, meaning that we solve a simpler problem where the variable is not integer, and we start branching, making choices, taking one variable, fixing it to 1, then fixing it to 0, and then going down, and this tree explodes in dimension. But when we finish exploration of the tree, we know where the optimal solution is. Probably some of you know about this. It's impossible to understand the details now, but what we have to understand is that to solve this problem, we need to explore a huge tree with a huge number of nodes, and eventually we get the solution. And to do that, we have to choose at each iteration one variable to fix. Like saying, let's try to go there and let's see what happens, and then there, and then there, and then there. And then there are all sorts of tricks that can make this more efficient. So what is happening in machine learning? Where machine learning applies here? Well, we have two very, very efficient techniques to do this. Local branching means that every time you try to go not too far from the current solution, so not to make too much of a long step. And this is very quick, and it's based on the length of the step that you make in this algorithm. Okay, so it's evident that this approach works very well, but we don't know what is the right step that you should take. On the other hand, there is strong branching that examines all possible solutions that you can take, all possible choices, and takes the best. This is, of course, very good, but it's very time-consuming because you have to solve the problem many times. So, how is this solved? Very annoying details, you can skip them. The only thing that we want to do is that we take a problem with constraints, this is our optimization problem, and we move it into a graph, which is a special graph, bipartite, etc., where each node and each part has some features that describe what is the state of that node in the problem. What is the value, what is the tightness, and other things that you don't want to understand now. And then what happens? We use graph neural networks, which is a special type of neural network where the input is not a vector, but it's a graph. And using the graph that describes the problem, we learn what is the best variable to pick according to a probability function, which is learned because we test the value of this problem while we go. And we have a set of instances that teach us what is the best way to do according to the status of the problem in each node. Similarly, you can do that for local branching, where you have, again, at each instance, a graph neural network that takes the description of the problem in that way that I explained, that is training, and then you get a pooling layer, and then you get the best K for that type of problem. So this is done offline. You have a set of instances, and then you solve this problem many times, and then you have this information that you learn and helps you to select the right K for the problem that you have. And this is providing very, very interesting results. It's in the community, there are doubts that this would kill everything, but there is evidence that when you use these methods, and if you invest enough time in learning offline, then the online algorithms that you use are much, much faster. So the trade-off between offline and online still has to be established, whether this is really convenient and for which type of problem. But still, the results are very interesting. Another interesting application is the selection of features in standard regression. Now we're taking a very simple case of regression, where that of course can be made as complicated as you want. But in general, the idea is that you want to select features to go from a large space where you have many features to a smaller one, because this is simpler, it's easier to interpret. it's more robust and has many advantages. And this is, on the other hand, it's counterbalanced by the idea of selecting outliers in models, because this is also something that it's particularly serious, because when we have our data, we don't really know whether this data comes from a single distribution, from a single environment, or whether it is contaminated by different samples that are not in the model that we want. Most oftentimes, we're not able to know this difference. And so we may want to find a model that doesn't take into account some outliers, but this outlier should not be defined after we find the model, because there is, of course, a strong dependencies among the two. So this has been, well, there are some considerations about zero norm regressions, where we find features, counting them. This is, of course, maybe a too much sophisticated reasoning about the fact that you want to minimize the zero norm of the coefficient vector. So for here, we simply have to say that we go from complex to simple, not just by touching these weights of our system, but counting it. So we can, with a mixed integer program, again, we are in the same setting, we can count the number of features that we're using, and we can bound them exactly. So we can say, do not choose more than 4, do not choose more than 5. And this is something that is very complicated to do, but can be done. At the same time, what we can do with outliers is to say, just get rid of 10% of your data and see what you find. And these two things can be done together in the same optimization model now for decent dimensions. Of course, not for large language models, but for cases that are in interest. The last example, please.
Sorry. Have you looked into Bayesian formulations like Gaussian processes? Because in some way, one of the nice things about Gaussian processes, for example, is that they also enable to do a lot of these things, while at the same time having basically a nice mathematical formulations that allow you to basically use implicit
it's a good alternative to this. I'm not sure that in many problems you can assume that you find the optimal solution to the Bayesian function model. You have to have strong assumptions on the distributions. So it is indeed a good counterpart. The idea here is that you formulate it as an optimization problem, and you can get to the optimal solution, combining both the features and the outlier selection. But of course, it's one approach, and this is what we like to study. These are the recent papers which came out. The last topic, I know, yeah, sure, it's something that we're doing now, and it's quite recent, and we're working on machine learning for forecasting problems. Forecasting means that you look at a time series and you want to predict the future of that time series. It is still a learning problem. It is a little bit different because the order of your feature is important. It's not like the feature at the realization of the time series in time. So it's yesterday, the day before yesterday, 15 minutes ago, and half an hour, 54% time ago. And one of the approach that seems to work well is combining forecasters, meaning that you take a time series, use different types of forecasters based on different methods, you put them together, and then you learn the weight that you have to assign to these forecasters to find the best solution. And you do that, of course, by learning by a neural network or something. So we still minimize the error, but we can use a number of well-established forecasting methods. Here there are the ones that I'm using in our experiments, there's 9 of them, and then try to make them move together. This is not new, this is what is often done. What we need is something which is a little new, and I think it has some interesting potential in general, because we solve this problem using 2 different neural networks. Actually, they are convolutional neural networks, because of course, the order is important. So it's like we're looking at if you look at a time series, it's like an image in 1 dimension, because it has an order. So you can apply convolutions to the different pieces of the network. But in this case, what is the input of the network is the output of the 9 base learning forecasts. So we take a time series, we predict the value, let's say from tomorrow, we have 9 numbers, and those are the features of our time series that go into the network. And in the network, 2 things happens. One is to learn with convolution of a standard, let's say, regression function. And the other one is to learn in this network from an optimization problem. So we solve this optimization problem, which is a feature selection problem based on some reasoning that is standardly used to do feature selection with trying to maximize the orthogonality of the features. So avoid features that are correlated because they have the same information. And this is done to train this part of the network. So to learn the way this optimization problem, which is a little bit time consuming, is solved. So on this side, we have the input, the forecasters, and the output is the solution of this problem. On this other side, we have the learner, the forecast, and the output is a vector that says what is the importance of each of them. But the nice thing is that these 2 outputs are combined together with softmax in a final outcome here. Okay, and why we do that? Well, because it works much, much better. But what works even better than that is that in our loss function, meaning that what we optimize here, what we minimize the outcome that we get here with the error that we make training. Then we minimize the error we make in classifying, emulating this model here. But also we maximize another component, which is the orthogonality between these 2 vectors. Meaning that we want these 2 models to find different things in the data. And this gave a very, very important improvement to the classification results. Meaning that we have 2 models that look for different things, that combine together, and what we want is that these 2 models operate on different information that is in the data. And this, of course, the nice thing is that it's trained all together, just in one go. So all of these things are optimized together and interact together. But again, it's done with vector variation, like every. So finally, I think we're done with time. I'm sure that it's in this nice villa there have been dances and people dancing valser in the past time. So optimization and machine learning dance happily together. They're really very interlaced, and optimization can still be a key player in machine learning, and still there are open problems that we need to remember while we're using machine learning successfully. On the other hand, the potential of machine learning in optimization is just emerging. How the study of the data that comes from the algorithm can be used to make the algorithm faster and better, something that has a lot of potential, but is not being closed at this direction. The implications are important for expandability, for energy saving, for generalization. On one side, because we can make better machine learning models, tighter, more efficient, more explainable. On the other side, because machine learning and help optimization in working better, and then go back. So that is a very, very interesting. So I think enough. Thanks for your attention. Everything was sufficiently digestible, and of course, hope to answer some questions. That is a lot of work in that. Actually, is one of the most studied combinatorial problem so far, also because it's a prototype of many others. There are works that try to do that, meaning try to learn what are the best configuration of the best decision along the algorithm for that. But really, I think that we're starting just now to understand what can be features of an optimization problem that can be transferred from one instance to the other. This idea of having this graph that represent the constraint matrix and then use graph neural networks is indeed, seems to be successful. But still, sometimes you just go from a different instance and from one problem to a different one, and what you learn is not so useful. So still, the idea that a combinatorial problem can be represented in an homogeneous way and in a space where distance between two problems means that they can be solved with similar methods is starting to emerge. You can sort of, see that in the distance from some sites, but it's not established.
Any more questions?
There are no stupid questions. Wait for my stupid answer, then we go.
I was wondering, you test this against benchmark sets also to make sure that you systematically understand, where the system is.
Yeah, normally, I mean, the tests are, of course, there are a lot of benchmarks. There are benchmarks for optimization problem to be solved, and there are benchmarks for optimization problems to be solved with machine learning. There are libraries that help to develop machine learning within mixed integer programming solvers. Let's say that whenever you discount the training cost, then it's always better. I mean, sometimes the improvement is very important, sometimes it's less important, sometimes it can be inherited according to the type of instances from one problem to the other, or even from one size to others. For example, you can use the models on smaller problems where you have these graphs that are used as an input, and then you learn the neural network that derives this graph, and then you take larger problem and you find for subset where you can take the same information. And so you learn parts of the larger problem from a smaller problem, and it is very advantageous. And then you use it and it works. Now, the only problem is whether it works so well. We don't know that, whether it's so well, and also how to discount the learning time that you have. If you need to solve a problem so many times, then you discount for the training cost, right? Like, for example, you spent a few years in training large language models, and now we're using them, so everybody's happy to have spent that money. But for some optimization problems, it's still not clear whether we can think about a general problem where we invest a lot of energy and then we use the information used to solve it, or whether these problems are so different from each other that oftentimes the investment that you make may not come back. So this is not clear actually in the research.
Can I get maybe you can answer.
Sorry. It's not a question.
Thank you also for the invitation to this lovely place. And so, I will mainly talk a bit about our recent work, about what we are interested in this topic. So basically, what we have seen in the last years is where like black boxes developed to solve certain tasks. And the question which always came up with this is whether we can really trust systems which we do not understand. On the one hand, in some areas we do it all the time, right? For instance, in drug development, we have developed procedures to benchmark, to monitor products without maybe fully understanding the biological mechanisms behind them. But in AI, it was kind of a very new area, and people thought, okay, maybe we have testing procedures, and there are some very famous people like Yann LeCun saying that testing is enough, good testing gives us enough trust. So in my opinion, testing is of course good, but I hope I can convince you that having some idea what's going on in the black box can help you to make your systems better and to get more trust into what's going on. I mean, one of the examples which I always bring is this Pascal VOC challenge, Visual Object Classification Challenge from 2005 to 2012. It was a quite prestigious endeavor. It was in the old days, kind of. But the task was to classify images into 20 different categories, like motorbike, bicycle, horse, and so on. The images were taken from the internet. It were like real-world images. Sometimes the objects were very small, sometimes they were occluded. So it was, at that time, at least, not an easy task. And every year, like, people compared their models and reported this performance. The performance was measured in average precision. And you see that for some classes, it worked good, like for airplanes, because most airplanes in the sky are kind of easy to detect because there are maybe no other objects. For classes like potted plant, where more like indoor scenes, the performance was worse, but in general, like, people improved, and it was quite prestigious to win this challenge. But at that time, nobody really cared and nobody understood what these models are doing. And what we did a couple of years later, we looked at some of the examples from this challenge and wanted to understand what these models were doing. So we developed, in the meantime, techniques to explain predictions. And our intuition was not to really figure out whether these old-day systems were good, but basically our idea was to compare these pre-deep learning-based systems with deep learning-based systems. Because the ones which I presented, they were mainly based on like classical feature selection and support vector machine techniques. And we kind of, we had a PhD student looking at the images, and what he found was really astonishing, because what we saw is that a lot of these examples the winning method of this challenge didn't do what it was supposed to do. So it was looking at the water to detect boats. It was looking at the trails to detect the train, and it was looking at the copyright tag to detect and classify horse images. And we thought, okay, what does the copyright tag have to do with the horse image? And our PhD student then looked very carefully through the data and found that like 20% or 25% of the training and test images have a copyright tag for the horse class, while it's much more underrepresented for the other classes. And the fun story is that very recently, this guy, the Lens, wrote us an email. So he became aware that his horse images are quite well known and quite popular. But basically, what this example shows you that, like, just from a single example, we could kind of find out that something is not going the right way. And of course, it was like a very lucky. We were very lucky to find this out. It was not a systematic analysis, but now we are more into developing more systematic methods to really understand whether our systems work correctly, and if so, we not only want to find these errors, these bugs, but also try to improve the system, to debug it. And of course, you could say the organizers didn't do a good job because they didn't check for this copyright tags. But as you can imagine, things are not better nowadays. So people always, also in this deep learning era, have the same problems, and there is lots of work showing different kind of effects, that there are some biases in the images. That, for example, for these melanoma images, often if the if the doctor like writes something on your skin, like a ruler or some kind of makes a marking, then the probability is much higher that you have a melanoma, because otherwise he wouldn't do it. So also here, like this ruler is used as a very strong cue for the class melanoma. Although I think in this case this is not melanoma. So these kind of biases are there, and we kind of wanted to develop kind of methods to understand what's going on, and also to use these explanations to curate our data and curate our models. So basically the first phase of explainable AI, so we started with this in 2014 or 13 with the development of this heat map-based approaches. So the idea that you have an image, for instance, and you have a prediction, and then you come up with an explanation showing you which part of the image was important for the decision making. And there are lots of methods in this kind of category. Most of them have been developed afterwards, but they are using different kind of systems, different ideas, but basically more or less do the same to identify this kind of contributions. And because this is like important for the second part of my talk, I would very briefly like to explain to you the approach that we developed, layer-wise relevance propagation. So the basic idea is that we are not, so we want to compute these heat maps showing us what was relevant for the decision. And we do it kind of in a step-by-step manner. So we use the structure of the neural network to get this explanation. So we start with the output. So we have the prediction dog. And then we ask ourselves, so how can we redistribute the prediction to the next lower layer in a meaningful way, reflecting the contribution of each of these neurons to the prediction. So we want to know like how much neuron J has contributed to the activation of neuron K, and this we denote as ZJK, these contributions. We do it kind of layer by layer, and of course there are different ways how to compute this contribution, and there is also some theoretical interpretation of what they mean, but I will skip that. But basically the main idea is that we have this, that we compute these contributions and redistribute according to these contribution values our relevance values step by step until the input. So of course the price to pay for this method is that you have to know the parameters, you have to know the weights, you have to know all the internals. So it's not a model agnostic method, but the good thing is that we not only have the explanation as an input, but we also have relevance values for all intermediate elements. So we know what is relevant for this prediction, which kind of channel has contributed to the prediction, which kind of weight is important. We will come to this later. Yeah, so this method has been applied to all different types of data, not only images, also text. This is just like a very old reference. I think now it's much more, but just to show you that it's not only images, but also medical data, time series data, and so on. And one example which I find very nice, okay, this is not a video, it should be a video, but basically what is this Atari games, this Atari game which were trained from DeepMind, and what you see in the video is that the computer is playing, and the ball is always kind of relevant, but you also see that the part over there in the left corner is relevant, and also the upper part here is relevant, and the machine kind of learned a very clever strategy to make a tunnel here and play the ball up, so to make a lot of points without risking to lose the ball. And we can kind of see the intention of the machine here, because it kind of regards this area as relevant, and if you see the video, you see that it kind of tries to shoot here to make this tunnel. And what we ask ourselves is, okay, how does this strategy learning progresses over training time? So on the x-axis you have the training box, and you see that the first thing the model learns, this green line, is the ball. So the ball, to focus on the ball, is the first kind of thing that the model learns, which makes kind of sense. If I'm not able to look at the ball and know where the ball is, then you will lose very quickly. Then the second thing the model learns is to track this pedal, and after 50 epochs or so, it kind of learns to focus at this tunnel area. And so you cannot, with this explanation methods, you cannot only like explain individual predictions, but you could potentially, at least for this very simple case, you can also track the learning behavior over time, which I think is very nice, and it's maybe underrepresented in the XAI community. So people should use more explanation methods to get some idea of the whole training process. I think this is a very interesting area. But basically, what I want to tell you in this talk is our kind of XAI 2.0 approach, because the question is, do we really understand what's going on when looking at this heat maps? And what I always said to people, because this is like an age predictor, so this woman was predicted 28 to 32. I always thought, okay, laughing is a feature of being predicted young. It seems like, right? So she laughs, and the mouth area is kind of important. So laughing is really important. So one can interpret from this that the model has learned to correlate kind of laughing with young age. But at some point, someone asked me, how do you know that it's really the laughing? Maybe it's the color of the teeth. She has also very white teeth, and white teeth also correlate kind of with age. And after thinking about it for a while, I thought, yeah, I mean, this heat map, this attribution map just tells us where something is relevant, but not what it is. It doesn't, so it's still a human interpretation of what it means. So in some senses, heat maps are kind of limited. And what we are recently wrote is like an extension of LRP, which I will go with you right now. So it consists of like 3 technical contributions. I will quickly go through them and then mainly focus on the applications. So basically, this is the old picture, layer-wise relevance propagation. You have the dog, you redistribute, and you get the heat map. And this heat map tells you, okay, maybe the nose is important, and the eye is important. And it's kind of a combined explanation. It's like an all-in-one explanation, right? But what we thought is that we know that in neural networks, especially on image domains, the higher layer channels encode meaningful concepts. This is kind of well studied. People study like ImageNet, networks straight from ImageNet, and reported that maybe some of these channels encode kind of parts of an object, other encode color and different concepts. So we thought, okay, maybe since we have the relevance of these channels anyway, so maybe we should try to explain in terms of these concepts. And assume that maybe this one is encoding concept eye, this one is encoding concept fur, and this one is encoding concept snout. Then what you can do is to have this LRP redistribution process, but condition it on the concept, which means by adding some chromatica delta here, you just let in relevance flow, which is related to this concept. And what you get by that is an explanation of the prediction dog conditioned on the concept eye. So this kind of tells you like how much the concept eye, encoded by this channel, has contributed to the prediction dog. And you can do this for all the other concepts. And what you get is like kind of a disentangled explanation, not an all-in-one explanation where you have everything in one picture, but you have now a kind of the contribution of all the different concepts encoded by higher level elements with respect to the individual prediction. And what is, yeah?
Because I'm lost. Right? How do you tell the system where the concept?
We'll come to it in a minute. Oh, yeah. This is the next part. But here we assume that we know that this guy is encoding the eye and this guy is encoding the fur. So let us for the moment assume that we know that. And then what we get is we can see like, okay, in this case, the fur concept has contributed even more to the eye than the eye concept, but we're not seeing it in this original explanation because the concept fur is spatially much more distributed, right? So the values are relatively smaller, but they are like on a larger space, but if you just measure the global relevance, so the concept fur, this guy is more important than the concept eye on the global. So by kind of disentangling this concept, you can kind of see and explain in more understandable terms and also like in more disentangled manners than just having a combined heat map showing everything once. And especially if concepts are on different spatial scales, this may be like confusing because the eye is very small and the fur is maybe much larger in the image, but in the end, it's kind of more important on the global scale. Okay, so the question is, how do we know what concept a channel is encoding? And this is a kind of old question or like an older question, and people use all kinds of different methods to find this out. So what people did is they wanted to know, okay, what does the channel kind of encode? And one kind of area of work, they try to synthesize input, maximizing the activation of this channel. So it's known as activation maximization. Other work try to find representative examples in the data set which maximize the activation of this channel. And by that kind of saying, okay, this example kind of a very relevant activate this channel, therefore they have to do with the encoding of this channel. And what we propose is not to do this search by activation, but by relevance. And the basic difference is that activation can be regarded as just a stimulating of this channel. So by using activation as a score, you find examples which maximally stimulates this channel or this neuron, irrespectively whether they are relevant for the further classification or not. So they are just like, they activate this guy, but maybe they are not really relevant for the task. So by using this activation maximization, as have been done like in all these works, you find out what maximally stimulates the channel, but it is not related to the task which comes later, right? So it doesn't have those context. And by using relevance values, what relevance does is it redistributes the prediction backwards. And by using this as a score, you find examples which are relevant for the task and which have something to do with this move, right? So it has kind of this task context, and therefore this is kind of the second contribution of this work. We propose a relevance maximization, and by that we can find examples which are relevant for this channel. So coming back to your question, what if we want to find out what is relevant for what does this channel represent, we can run relevance maximization and get some examples which represent us a relevant concept. Of course, in this way, we have to do the last interpretation. Or if you have labeled data, if you have very specific concept labeled data, then you can, of course, do it automatically. Or if you have like a second neural network labeling these images and saying, okay, these images represent this concept, then you could do this automatically. In this work, we kind of looked at it and tried to find like what does this concept has in common. And the third contribution is more like technical. So assume we have this reference images, and okay, these 6 images are important for this channel, but still it's very hard to see what do they have in common. So what is it really what they encode? Is it like, you may say, okay, is it the bird? Okay, but this is not the bird, but it's still relevant. This is also not the bird. So what do they have in common? And what we did is we kind of yeah, we use this receptive field to just zoom into the area which is kind of covered by the channel, and you can also compute like heat maps and extract only the relevant part, and by that you can really from this reference image, which you get by relevance maximization, you can find out what is the relevant part in this image which plays a role in this classification and is encoded by this. So this becomes more clear when we see it all in common. So we have like an image, it has been classified as some kind of bird, and what we do first is we find the relevant concepts. For example, we look at the last convolution layer and extract like the 5 most relevant channels. We can do this because LRP gives us relevance values for all the elements of the neural network. So we can do it we get this for free from LRP. So we find the 5 most relevant channels. This is step 1. Then we can compute these conditional explanations, showing us where does the information come from encoded by this channel. And then we can also visualize the reference samples by relevance maximization. So this kind of answers the where question, and this answers or gives you a hint of what does this encode. Does it encode the color? Does it encode the shape? And for example, here for channel 10, you see that all these reference samples have red color, which indicates that really the fact that this bird has really a red color over here is important for the prediction. So it's not only that it's like a stripe, but it's really the reddish color which kind of triggers channel 10. And channel 10 is among the 5 most relevant channels for this prediction. So you can get explanation on a semantically higher level, on a more human understanding level in this case. And one cool thing you can do with that is even you can track the whole inference process downward. So we start with the prediction, and then we ask ourselves, okay, what is the most relevant concept contributing to the prediction? And then we identify channel 102, and then we ask ourselves, okay, what does channel 102 represent? We get this images by relevance maximization, and it seems that this channel is kind of representing animal sitting on a branch, because you have like some monkeys or birds sitting on a branch. So kind of semantically, this is what we kind of derive, or this is what we interpret from this channel. And then you can ask yourself, what other lower layer channel have contributed to this encoding? And then you identify maybe channel 506 and channel 51, and the one which represents more like colors and feathers, and the other one is representing more horizontal shapes. So this is probably important for encoding the stick, and this is more important for encoding the feathers or kind of part of the animals. And you can do it like also you go down to the low layer features, and you can not only allows you to explain in terms of input relevances like the attribution maps did, but it allows you to explain the whole inference process and also take into account the representation of the model. So what does the model represent? What does it encode? And how did it contribute to the prediction? What individual elements of the model were important for this individual prediction? And how do they interact with each other? So how is the one built from the other? One final example we found, this is also mapping from ImageNet, where we have a class safe or Tresor, and we found, okay, there is some strange Chinese characters in the middle. And we ask ourselves, so what channels in the network represent this Chinese characters? And what we did is we found the 6 most relevant channels in this region. And these are the channels, and apparently they represent some kind of Chinese characters, or this kind of shapes. And then we thought we did some kind of reverse image search. We asked ourselves, for what other images are these 6 nasty channels also relevant? And abracadabra, we got like images where they also have these Chinese characters because these nasty channels are also relevant for these images. But what's even more surprising is that we also got some images of a puma in the spider web, where these channels are also relevant, but there are no Chinese characters. But to the model, like the very thin hair of a puma or the very thin spider web looks like a Chinese character. It's kind of encoded using the same channels because the Chinese characters are also very thin strokes on the background. So what you can kind of derive from it is that just removing these channels wouldn't work, because you would maybe get rid of this problem, or at least be more trustworthy with this respect, but you would maybe take away some ability of the network to detect pumas and spiderweb. So you have to be very careful also how to debug the network, but not like maybe solving one problem, but not introducing a problem for other classes. And what we recently propose is kind of a explain and improve framework, explain a debug framework where we, in the first step, identify the problem, identify the weakness. So we can do this identification either in image space. We can do some clustering, for example, of the heat maps, or we can do this in embedding space. We can do some clustering in the concept space and then show them representative examples for each cluster to the human, or show the outliers to the human. And maybe the human says, okay, this is an artifact because here is this melanoma prediction, and apparently this is like a cluster, a band-aid, and it should be part of the melanoma prediction. So this is like an artifact. Please get rid of it. So we kind of first identify. Then the second step is to model this problem. What we did is we identify these artificial samples where this is the problem with band-aid, for example. And then we identify the clean samples where this is not a problem and try to fit a concept activation vector in hidden space, describing us the problem. So this concept activation vector kind of shows you the direction in hidden space where this kind of artifact behavior occurs. And then, of course, you have to unlearn it. There are different methods to force the model to correct. So you can either like project this direction out, or you can retrain the model and forcing it to not assign like relevance in this direction. So there are many different methods. There is this right for the right reason to work. So in this paper, we have, I think, used 2 or 3 approaches, and then you can evaluate how successful you were in removing this artifact. And for that, we use like a Poisson data set where this is the case at the clean data set. And in this work, we kind of did it iteratively. So we first removed the skin marker. So this is also the melanoma data set where medical doctors sometimes put some skin markers around the melanoma. And then we force the model to unlearn it. So here we have this artifacts, and here the model kind of unlearned it. Then we have the second round, and we say, okay, there are also some classes of band-aid, which is problematic. And this is still part of the model decision-making. So we force the model to unlearn it. You don't have it here. And then we have this ruler. So medical doctors sometimes also write this, put the ruler on the skin. And you see that this is also relevant in the decision-making. And we force the model to unlearn it. So iteratively, kind of, we corrected the model. And we use the explanations as kind of a filter, as a magnitude, a lens of magnitude, showing us where is the problem. So instead of looking at the data, which would be, I think, more complicated, we look at the explanation, and explanations kind of told us, so what is the decision strategy, and then we developed methods to unlearn things. Yeah, we have also some review on this. I think this is very interesting. The direction of using explanation methods to improve your models. So not only explaining for its own sake, but really making something better with the explanation. And the last few slides is more like even go one step further, like auditing certification of models. So we are in some initiatives where we try to understand like how would such a certification, auditing, benchmarking process look like? So we're coming back to, do we trust our black boxes? Can we develop similar procedures which were developed for drug development? Can we develop similar procedures to certify the correctness, robustness, trustworthiness of AI models? We are doing this, and also like what role explanations can play in this auditing process. We are also some international initiatives with the WHO, the ITU. Now there was established like a global initiative on AI for health, which we are part of, where we really try to build some benchmarking platform using explanations. Of course, explanations is not the only dimension when it comes to trustworthiness, but I think it's an important part, and we are trying to understand these relations. And yeah, with that, I think I'm very much interested in combining these different levels of XAI. So we have this heat maps, this attribution map, this data set level explaining in terms of data what is important in the image. We combined it with model level XAI, so which elements of the model are important for the prediction. And we also try to combine it with the human level XAI, where the human can give feedback, where the human kind of can play around with it in an iterative manner. And I think with all these three dimensions, we can come up with better models in the end. We have also the books and toolboxes for all of that. And yeah, with that, I'm kind of done, and all the work is on our website and also my personal website. Thank you very much.
Super cool work. I love the heat maps, how you generate them. But I have, I guess, I want to philosophically challenge some of your assumptions. Mm-hmm. So in the way that we currently train basically classification, for example, algorithms, as we've shown, what at the end of the day really matters is the relative ranking of different classes. While the type of basically heat maps that you obtain in this moment don't really consider other classes with respect to the one that you are examining. So I think it might be very interesting to basically also consider basically the heat map in the context of basically multiple outputs. So you could imagine, for example, if you have a heat map where if you are comparing, for example, a horse and a car,
I fully agree with you, and I always try to make people aware of it, that there is no one explanation. Often have people that have the idea that there is one true explanation, but it always depends how you pose the problem. Do you want to explain why is this a horse and not a car, or why is this a horse and not a cat or something? So you can, this contrastive aspects definitely are interesting, definitely can be integrated into this. There is also a contrastive version of LRP. So I think from a methodological point of view, it's very easy to integrate these contrastive aspects, and I'm very much agree with you that one should carefully, when investigating things, one carefully understand what I am explaining and maybe how to pose the question which gives us the most relevant insights.
Yeah. So in this case, I don't know if you've already done it, but instead of using the maximum activation, you could use the maximum difference of activations between two images, and then basically get out heat maps of, okay, this is what the model is looking to actually distinguish between these classes.
I'm not, I mean, there is this was not our work, there is a contrastive LRP version from some guys from Munich, but I'm not quite sure if they do it in this way, but this is, I think, a good idea. So I will think about it, and maybe it will be, in the end, it will be the same what they are doing, but I have to think about it more.
Thank you very much. I think it's important. Explanations, we discussed this, it's a very good explanation of what, and then you have these new and of course your approach is somewhat close to because it relies on the data set and on all elements of the data set. While humans, of course, are not close to it. So their concepts
somehow might be completely different. Of course, you have shown us those examples, that make sense to the audience, that has a very general background. But then, of course, there are other examples that show Chinese things, copyright and so on. So I was wondering, I still believe it's super valuable. I was wondering if you have sought to find cross data sets.
Yeah.
So you use concept actually from all data sets to explain, the content from those to explain, things that you see.
Yeah, I think this is very good point. I think one of the advantages of our approach is that you are not forced. First of all, you are not predefining the concepts, but it's like an exploratory approach. And secondly, you are also not forced to, or you're not limited to use the training data. You could also use another data set where, for example, you have different images containing different colors, different textures, different shapes. And I think this would allow you maybe to have explanations in a more understandable way, in a more controlled way, if you have such a data set. We didn't do this here. We used, I think, most part just the training data, but if you have such a data set, you could use it in any way. But the second point is, of course, that for images and for image classification, for object classification, it's much easier to understand what's going on, because you have an object, you have a nose, you have ears. If you have other types of data, other types of classes, the concepts can be very hard to understand.
No, but I think it would be also interesting to probe actually maybe the users, in a sense, what are the most likely concepts that they are. Of course, medically trained person, you have different concepts than actually the layman. And now the question is, how would you use your approach actually to change the explanation?
Yeah, definitely. I also believe in this interactive XAI idea that explanation is not like just, okay, here is the explanation, that's it. So, but it's more like a process, and it's also the user has to ask the right question and prompt the right, and then you will get some insights and understand what's going on. But it's really like a process. So I strongly believe in that.
Thanks for the perfect instance. Actually, I have two questions. This one is, there is not one expression, there are expressions. Is there an objective way of comparing expression, judging this expression is better than the other expression? And second is a much simpler explanation like the following one. We choose one of the last layers of the neural network is a teacher network, and we search in the true data for the most similar images.
Yeah.
Full search, the electronic classification, so taking the most similar image. To instead.
I mean, so the first question, I think there's many work on how to evaluate explanation. We have some work using where we created a ground truth benchmark, where it's a synthetic controlled experiment where we kind of know what is relevant, and then you can kind of control to what you get. And there is also like our Quantus work where we implement, I think, over 30 different metrics which have been proposed in the literature, and we categorize them in 6 different categories. So you can do kind of evaluation with respect to different properties, and this is kind of what we implemented here. And this is, I think, there is the evaluation problem is also tricky, because you can evaluate with respect to different properties, and depending on what you ask, maybe some method could be, if you, for example, take sparsity as a property, then maybe one method is more sparse and the other is less sparse. But you should be aware that there are like this different properties categories of evaluating, but I recommend to look at Quantus. And the second question, yes, I also think that in certain cases, especially in the medical domain, people are very used to like explaining by example, saying, okay, this is maybe here's cancer because I saw like 5 similar cases before. And I think, I mean, we try to kind of combine it in this new CRP approach where we give this reference samples, but I wouldn't. I think these approaches are kind of complementary, right? You can the one explains you what is important in this particular input, and the other tells you what is maybe the most relevant training data points which have lead to this decision, or what are the most similar examples. I think this is complementary information, which in some contexts can be very valuable.
Do you think that this method can be applied also to transformers networks that are more complex?
Yeah, we are currently working on that. It's more tricky because you have like this, the products and yeah, I mean we are trying our best and
would it make sense? In a sense, in classification, you can say, well, we don't classify on the basis of false premises, but in generation, what would be the false premises for the generation?
Okay, but the one thing is the difficulties with the architecture. The other thing is how to formulate it for different types of problem. I think this is even more tricky. So what does it mean to explain a generation process? I think there has not, most of this work has been done for classification. It's also very interesting to see how these concepts can transfer to other types of reinforcement learning, segmentation, generation, and I'm also very, very interested in that. We even try to, I have some collaboration with Jens Eisert, who is one of the big quantum guys in Germany, where we try to make quantum computing explainable, but it's tricky. It's tricky.
Very last question.
Yeah.
Just one for me. I was wondering whether you're considering the use of synthetic data challenge evaluation.
I mean, here we have like a synthetic data set for evaluation, where you can kind of create examples where you know what is relevant, and then you can compare what you get. Built from the explanation so that challenge them. Yeah, so that's a good idea. We haven't done this systematically. It's definitely a good idea to try to have a loop and say, okay, we explain and we improve, and maybe we use synthetic data for that.
Ambulance that looks like a loose service has a well spot. Now, if that ambulance has a loose spot that is solved and is perfectly visible that you have that ambulance, even if you don't have it.
Yeah, but in this case, I think it's not like an error. It's not like a problem, because this channel is just responsible for extracting maybe red color or red stripes. So it does a good job in doing this, even for ambulance or for a rooster. So I think, I mean, this is how neural networks kind of work. The one channel is extracting this and the other extracting that, and then it comes together. Yeah. But I'm definitely interested in designing approaches in this XAI model improvement, that you have it in the loop, and then you have try to make your models better, more robust by using explanations of information derived from explanations. I think this is a very promising direction.
That's great. So first of all, let me thank Wojciech and all